Okay, let me start our last capitalization. Our speaker, Andrey Trepalin, he will talk about minimal services over finite field. Thank you.
Thank you. I'm very glad to have a talk on this conference. So, as you heard, I will talk about minimal cubic surface of finite fields. The name of this talk is quite like permutation of Debar's talk, and it's about joint work with Sergei Rybakov. He's here now. What do we do?
Are you going to use the beautiful form? Are you going to use the beautiful form?
No, I'm not going to use beautiful forms. All formulas will be not beautiful today. Not today, in this talk. Yes. What we have? Let X be a cubic surface into 3 over the finite field FQ. For simplicity, we'll place that Q is not divided by 2 and 3. Then the Goulart group of algebraic closed mass of Q naturally maps to the Y group, which acts on the Picard group of this cubic closure. We call the image of this group by gamma. It's well known, as a result of Swinton-Dyer, that there is 5 possibility of cyclic subgroups of the group of S6, such that the cubic surface, such that invariant Picard group is equal to Z. These subgroups of order 3, 6, 9, 12, and one more 6, such that this group does not contain this group of order 3, and all other groups are containing this group. Yes. So there is an element in the group, the while group of E6, such that of order 3, such that invariant Picard is equal to Z. What do
you told there things that was done by mine first?
Huh?
So you told there things
what first was mine?
Mine was.
Minus, it will write in his book that first was Swinton-Dyer. So we're writing down. Swinton-Dyer and what do we do? It's just combinatorial results that there is 5 cyclic subgroups that the car is Z. But we want to construct explicit examples of cubic surfaces such that the image of the Goulart groups in the Weyl group will be one of these possibilities. We show that all these possibilities can be achieved for some field K, FQ. So, well, let's start. Well, if we have arbitrary cubic surface, we don't know what to do with it. We can use computer, find lines on it or something else, look at the Goulart groups. But when we go to other fields, this will not. So we don't should to consider arbitrary cubic surfaces. We'll consider special. Let's start with a simple example, which already arises on this conference. Example. Consider a cubic surface x cubed plus y cubed plus z cubed and cube equals to 0, where Q is order of the field equals to 3k plus 1, and so the third root of alpha is not in our field. Yes? Then we know for this cubic that
This implies
that so if Q is the 3k plus 1, then either all cubic roots of alpha are lying in the field, or all are not lying in the field. We choose alpha such that it's all aren't lying in this field. So
what is F?
F,
Little f. Little f not there.
T. T.
it's
Oh,
T.
that's T.
It's T. Yes,
Oh,
it's
okay.
T. Just for the coordinate.
Oh,
X,
okay.
Y, Z, T.
Oh,
Yes. For coordinates. And for this cubic surface, we know that all 27 lines are defined over K. Moreover, the Galois groups act on this line by permuting the three lines which intersect in a point. What do we have for this example? Note that at first two observations. One, for this surface, we have a huge group of automorphisms. So we can multiply any coordinate by the third root of uniting. This will be third root of uniting. Yes? And we can multiply any coordinate by this root. And the second, we can commute three first coordinates. So automorphism group of this cubic surface is at least cyclic group. This group can give product to S3. So we have huge group of automorphism. And the second idea is that on this surface, on this closure, we have 18 Eckart points. Eckart point is a point where three lines on this surface meet. So, what's the good about this example? Yes?
Is it true that the restrictions we have already implied or imposed on our field imply that omega is in the field?
What? About characteristic, you say, yes? If characteristic is not 2, then here is 18 Eckart points.
Oh, there's a question about the cubic root of unity.
Cubic root of unity, it's important that Q is 3k plus 1.
And then it, then it
Yes, yes. If you have the Q is 3k plus 1, then this omega lies in our ground field, obviously. So, for this condition, we have and 18 Eckart points. It's if Q is not divided by 2. If the characteristic of field is 2, then we have 45 Eckart points, but we don't consider characteristic 2 in this. So, what do we have? We have huge group of automorphisms, and this group maps to the line group E6, and moreover, this group commutes with the subgroup gamma, which is the image of the Galois group. So when we have automorphism group of cubic surface, some automorphism acting in this, then the possibility of elements of the Galois groups acting on the Y group are less than if we don't have such a. And the second thing, that's Eckart points. Since we can find such points on a surface, and then look at these points, write down tangent equation of tangent plane, then find some lines on the surface, and so we have a point to start our computation. Well, so now we see we have Fermat cubic with 18 Eckart points, and we realize this case with some conditions. So this is the idea to consider a cubic surface which these Eckart points and the groups of automorphisms acting on this. Well, So, is it everything is clear for this moment?
So the example says that the first case is possible at least when q equals 3k plus 1.
Yes, but now we construct more huge construction. Well, let us consider cyclic cubic surface. Cyclic cubic surface is a surface which is given by equation p xyz plus t in the third degree is equal to 0. What do we have for this surface? At first, we have projection natural x to p2, well, we just forgot the last coordinate. We have projection to p2, which is covering 3 times to 1, and the boundary divisor is an elliptic curve E. Also, if we have q equal to 3k plus 1 and omega, therefore in fq, we can consider this projection like getting a quotient by the group generated by the element g, which x tends t to omega t. Yes, we have an anthropomorphism to this surface in this way. Moreover, the interesting thing that on such cubic surface there is 9 Eckert points, at least 9. This point can be achieved by getting preimages of inflection point on E. Yes, if we consider an inflection point on our elliptic curve, then getting preimage here, we have a tangent hyperplane which intersect our x three lines passing through the point of tangency. So we have one-to-one correspondence to Eckert point here and the inflection point on E. What do we want to think about? Well, this element, the action of G, which maps T to omega T, the action of this element on the group, image of this action in a while E6 is conjugate to this element of order 3, such an element which is minimal, for which the cubic surface will be minimal. And so we want, at first, we want to have in our Galois group, an image of the Galois group, element which is acts like the geometry group G. And then we want to try to explore this group for other cases, the second, the third, and the fourth, and look what can we do there. So this element there has a invariant section here, which is t equal to 0. It's an elliptic curve which contains of fixed by G points and which contains also all 9 Eckert points. So therefore this element acts trivially on Eckert points and contact on our elliptic curve. Well, 9 inflection points on this curve. They form something like a thin plane over a field of 3 elements. That means that if we draw a line through a pair of points, then the one other point lies on this line. Let's consider these lines. The first statement is that if there is the group gamma is the case 3. Then if in the on leaf there is 3 conjugate by gamma inflection point, which don't lie on line. Well, how to prove it? Let us consider, assume that the group, there is 3 conjugate inflection points which don't lie on a line, but the gamma is not 49. Then in our group gamma, there is only one subgroup of 49 in while group up to conjugation. So if there is not a group of 49, then we have an element of order 3 in the group gamma. And moreover, this element produces these 3 conjugate points. So we can consider 1 minus 1 curve on X, which passes to preimage of one of these points. And also consider its images after under the action of gamma. So since the element of gamma has order 3, then this is invariant, and moreover it equals to minus kx. But if it equals to minus kx, then this sum of these 3 curves, they line in a hyperplane section. So we can consider intersection of this hyperplane section and our cubic and map it to P2. Then we have line on P2. And this contradiction shows that if there are 3 conjugate inflection points not lying on a line, then there are elements of order 3 which computes these 3 points. But the orbit has length 3, thus we have an element of order 9 here. So, and vice versa, conversely. So to construct an action of this group, we just have to construct an elliptic curve on plane, which has 3 inflection points which don't line on a line and conjugate by the action of Galois group. By the methods of number theory, we do this if the Q equals 3k plus 1. It's non-trivial theoretical number result, and I think I don't have much time to do this. So, now we want to construct 3 other actions. Yes? I write down here conditions. In any other cases, if we don't have an element of order 9, then one of these points are defined over our field FQ. Yes, let these points be defined over FQ. First, assume what can be about these points. Assume that 4 lines passing through these points are also defined over the field FQ. Then lemma. One more.
Each of the 4.
Yes, each of the 4. Lemma. These points will be P. If P is defined over Q and 4 lines passing through P are defined over FQ, then either all other inflection points are defined over FQ, all of none of them are defined. Well, let's prove it. Assume that one more point is defined over the ground field. Then we have that this point defined 2, since this and this are defined, and this is third one. Or what else? We have consider any other point. We'll try to map it to something else. Then, for example, this point should go there, and it's impossible since these lines are defined over our ground field. So this is quite simple dilemma, but it says that, what does it really say? If all 9 points are defined over FQ, then we have the first case. If 4 lines passing through P are defined over FQ, but points are not defined, then we have case 2. And what's about the fourth case? The third case we consider in our previous lemma.
Why do we have case 2?
Huh?
Why do we have case 2?
Since we have these points are defined over all these n9 points are defined over FQ squared. Yes, in the case 2. And now to define every -1 curve on the cubic surface, we just want to go to the extension FQ6. So we have Galois group of order 6 acting on the set of -1 curve, and this Galois group contains this element. So we're in the case 2. And now assume that no one of these lines are defined over FQ, but all these lines are defined over FQ squared.
So, but what's the difference? You just write down the polynomial P so that all 9 points are defined over Q, yes? You just write down a particular polynomial P for which all inflection points are defined over Q, and say that in this case you have solved case 2, yes? You have constructed the action.
I say that if these 4 lines are defined.
Okay, I understand it, but so
Yes.
how do you use it after all?
After all, I write down the equation.
So,
I write down our equation which will satisfy this condition, which I write down before. So the last condition for the fourth case, if lines passing through P are not defined, no one of lines are not defined over FQ, but defined over FQ squared. Well, what is this case? In this case, one can check that the order of element action here will be 4. How do we use? Let's consider an element here. Assume that the order of group of action here will be 2. Then this pair will be invariant under the action of group. So we have a defined over FQ line, and this point, the third point of intersection, will be defined over FQ. But in this case, we have 2 points on this line which defined over FQ that predict our conditions. So if we have no line defined over our field, but defined over its quadratic extension, then we are in the case 4th. Then here we have 4 lines of P, either all is defined or undefined. Well, now we've given an explicit construction of these conditions. So we quite not different string, but to have a result, we should write down the formula. Well, let's consider a cubic surface, cyclic cubic surface, which is given by equation s cubed y plus this y squared plus c y cubed plus y z cubed squared equal to 0. Well, what do we have for this surface? First, we have an inflection point. Inflection point 0, 0, 1, 0.
So is the elliptic curve you are based on, or
Oh, yes, it's not a elliptic curve. It's a cubic surface plus t. But if you just destroy this t, then you have a question of elliptic curve. So 0, 0, 1, 0 is not inflection point, it's Eckart point on the cubic surface. And the tangent space Gipper plane on this at this point will be y equals to 0, and the equation of three curves passing through three lines plus passing through this point will be a cubed plus t cubed equals to 0. That is three lines through t. Well, we have this group of order 3 as image in the while group. We should have that this equation shouldn't have any root. So we say that q is through k plus 1 again, and we say that the third root of a don't lie in fq. This is the first condition. Well,
this more or less boils down to your first example, right?
huh?
This is more or less the same as you said in your
Yes, yes, it's some looks like the first example in some sense. Well, but what we should do now? Now we should consider the lines, point lines which pass through these Eckart points and through other Eckart points. So to find these lines, we should forget about t, then write down the Hessian of this equation, intersect it with the now elliptic curve, and find the points. By computation, we have that equation of 4 lines passing through points 0, 0, 1 will be 3 squared is 4 to 6 AB squared squared plus 12 AC x y cube minus this square in the plus. So now we want to find A, B, and C such that satisfies the condition of our two limits. It's quite simple, since we can say that B or C equals to 0. Well, first, assume that B is equals to 0. Then we have equation of 4 lines passing through P. Ax in the fourth plus 4c x y in the third degree equal to 0. If we want to satisfy these two cases, first or the second, we should say that this equation have all 4 roots. Thus, the number minus 4c divided by a should be a cube in our field. Yes, we can find such c. We fix a at this place, and now we look at c. We can find such c that this number will be cube. Well, let's now consider a pair of points lying on one of 4 lines. Consider the line is equal to 0, then the pair of the point inflection point on it will be given by the equation y plus c y squared plus z squared equals to 0. Since if you here say that x is equal to 0, we have just these two members. And it's so. So we have two possibilities. Either these points are defined over FQ or not. And these possibilities are just C is square or not. But we can, among such a number C, for which this number is cube, we can choose squares and not square everything. So by choosing C, we can construct examples for these two, so for both this case. So we construct these two examples. Now the last one. This was when this was here. All four lines passing through P was defined over our main field, and now we should construct an example where all these four lines are not defined over FQ. So how do we do it? We just say that C equals to 0. Well, if C equals to 0, then we have equation 3a squared x4 plus 6ab x squared y squared plus minus b squared y in the fourth equals to 0. This is equation one can easily compute it and say that ax squared equals to b minus 1 plus minus 2 root of 3 by 3 y squared. What can we say about it? If this root doesn't lie in FQ, then we have immediately that all lines are not defined over FQ. And if this root lies in FQ, then we can find B such that solution of this equation are not defined over FQ. So by choosing B, we can find such equation that its solution are not defined over FQ. And so by lemma, which I have destroyed just, we show that in the first case, for Q equals to 3k plus 1, we can construct such cubic with this below root. Yes? Well, what can we do else? At least the last case. Let's do it.
Now you are just trying to guess an elliptic curve.
Huh?
Now you are trying to guess a plane cubic curve such that the configuration of inflection points has some properties.
Yes.
And so you find it in basically in some cases depending on Q. And do you know that like this particular problem is solvable or not solvable for
what?
3k plus 2?
3k plus 2, I said about it in the end. So now we construct examples for 3k plus 1 for all these 4 cases. We have also 5. Of course, this construction which I do now, my previous concept, don't work for 3k plus 2. Yes? But we have more constructions.
You mean the particular equation doesn't work for 3k plus 2?
Not particular equation, but whole construction of cyclic cubic surfaces. If you consider it, the other surfaces here, you can, this equation which I just destroyed, yes, this equation of 3 lines passing through 1 epoch points. It have, for 3k plus 2, it has 1 solution. Not 3 and not known. There are some.
I don't understand, but this relies on having like x cube.
We can
Having x cube in your equation. Can you possibly have?
No, I cannot deform this equation since I have to have t cubed isolated without members of t over something or t squared over something.
But you can mess
Because
up
this
with
side is a cubic surface. It should have a t cubed as a isolated member.
Can't you mess up something with x?
I think.
Well, I mean, what I'm trying to ask is, do you know, like, kind of theory?
I say about other conditions. Moreover, in this case, I say at the end of talk. So that's not all that I can. Yes, but first we should do the last case, which we don't do. Well, what about the last case? In the previous construction, we use a cubic surface with 9 Eckart points, and then the first example with 18 Eckart points. But we can use cubic with less number of Eckart points. Let's consider a cubic surface. Cx s square minus lambda y square plus Qx vy zp plus z cubed plus alpha t cubed equals to 0. Yes? What do we have this? We have a group action on this surface. This element G sends x, y, z, t to x, y, omega z, omega square t. You see that other element of order 3. Really, this element acts on the while group like an element of order 3 which contained in this group. Overall, what we can say about this element, that centralizer of element G in the group Y of E6 will be a group isomorphic to the following. You can see that order of this group is 108. So it's quite a huge group, and moreover, it contains lots of cyclic subgroups. What also we can say for this surface? For this surface we can see that there are 3 Eckart points. And 3 Eckart points are given by equation z cubed plus alpha t in the third equals to 0. So to find this group, we should have 3 Eckart points are not defined over FQ, no one from these points. So again, we have Q equal to 3k plus 1. And alpha is not cube. Well, so you can see that really the centralizer here is much more bigger than in previous case. I don't write it in previous case, but then it will be less. And so really to find proper group, a group which we need, we have to satisfy some huge conditions, which I'll write down now and say which objects on the cubic surface they correspond. These conditions look like first z cubed plus alpha t cubed equals to 0. No solutions. Then Cx square minus lambda y square plus Ux plus Vy cube. Let's say alpha. One solution. then 6 x squared minus lambda y squared. One solution. And the last equation for alpha, mu is parameter here, is variable u squared minus v squared dot lambda u squared minus 2uc mu minus c squared is equal to 0. Three solutions. Well, really to prove it, it's a quite big calculation and I omitted it. But this equation corresponds to Eckert points on x. This equation corresponds to -1 curves passing through one Eckert point. One of these Eckert points. This corresponds to fixed point of this element, and this equation corresponds to some member of linear system -2kx, which are invariant under the action of this element G and pass through a pair of fixed points defined by this equation. So, final condition, you should look on the geometry of our cubic surface to find some elements. But we can write down an equation which satisfies all these conditions explicitly. I think this is the better place. Its equation will be 2 alpha squared x minus s squared minus lambda y squared plus z cubed plus alpha e cubed equal to 0. Here alpha is not a cube in FQ and lambda is not a square in FQ. So just a simple equation but a big explanation for this equation. So now what we have? We have that for the order of fields 3k plus 1, we construct all these group as a subgroup of while. The image of Galar groups in the while group. But one can ask a question. What about other cardinality of our field? If Q is not equal to 3k plus 1, and for example, it's 3k plus 2, or if characteristic is 2 or 3. What else also we know? Well, I have 5 minutes. I think that it can write down. One more construction, but not all. The construction is the following. That here is the last construction which has 3 Eckert points, and now we go to 1 Eckert point. This is cubic surface given by x y plus y z squared plus z d squared equals to 0. What do we have in this situation? We have an element of order 2 acting, of order 4 acting on this surface. X, y, z, t maps to x, y, minus z, I, t, where I is the fourth root of 1. Well, x at least over fq squared. Maybe not over fq this section, but over fq squared it is, and over fq for any q, there is always act an element of order 2, which maps t to minus t. What also we have for this surface? We have Eckert points. 1 Eckert point. It will be 0, 0, 0, 1. So, applying construction like in the previous 2 cases, for this one and this one, we can prove the following. We can construct examples of cubic surface which satisfies the conditions of the cases 1 and 2 for q equals 4k plus 1 in the first 2 situations. And in the fourth situation, we can construct a cubic surface satisfying the conditions of this for any q which is not divided by 2. So almost everywhere.
Q is the prime of
Huh?
Q is the power of prime.
Q is the power of prime, yes. We can characteristic is not two. What? Just I want to say. Yes. Yes. So you see that there are some cases which I don't know how to construct or how to say that you can construct this one, but we constructed both cases for the case Q equals K plus 1, and this case for almost every Q. Yes. Thank you.
Thank you very much. Any questions?
How about other debates?
Other debates? Well, Sergei
Either
construct.
one or two.
Yes, Sergei construct for the degree 4 and more. All these cases, all
This
cases.
is much easier.
And for the
Loading is easier.
no,
High degrees are high, guys.
I don't know. But
One and two.
Huh? Why do you think that
One and two.
1 and 2? I will think about it. I don't think yet because now I'm thinking about the past case. But the group is bigger, but we find some ways, I think, to deal with it.
So this case is based on some distinguished property that's in the chapter, like a number of points and number of lines.
Number of points or number of lines is always 0.
By some
You know, the number of lines is always 0. Number of points is you can write down zeta function, but I don't know what to do with it.
Actually find the population of something.
Newton Bell was originally integrated by zeta functions. So he classified zeta functions, and actually the table from the minus book gives you out of this data you can compute the zeta function. So it's just use the table.
Zeta function is determined by the section.
Yes.
So the thing can be determined by number of points or some case maybe it's possible to construct and just count these points.
So the question is, can you do it another way around?
Well, it's very difficult to construct number of points, to compute the number of points of this equation.
Well, if it's cyclic, it's not bad. It's just the standard method. You basically have three solutions, one solution. It's similar to number of points.
Okay.
Very interesting.
No question. Okay. Let's think again. 10-minute break. I have a small announcement.
Yes.
So, if you have been to dinner yesterday evening, recall that Oля faced the whole build just for us not to make a mess on the counter. And if you didn't yet reverse her, remember that she waits.
So this